Thank you very much. I'd like to thank the organizers for inviting me to this meeting. I should say that it's a fairly new experience for me to be at a meeting on active matter because I'm generally not very active. And also because my field of research is quantum condensed matter theory. So this is really a bit of a departure for me from what I usually do. Um, so the work that I'm going to talk about today has been done in collaboration with Nisarg Bhatt, who is a PhD student at IISc and in the audience. And of course, I wouldn't even dream of venturing into an unknown field without guidance from the master himself, Sriram, who also is obviously in the audience. So the work that I'm going to talk about is currently being written up and hopefully will be on the archive sometime soon. So before I get into exactly what we have done, let's just start with something that most people here would be familiar with, which is a classical Heisenberg chain. So you can just think of this as three-dimensional rotors of fixed length on a one-dimensional lattice. And the simplest Hamiltonian that you can write down for this system is something like this, in which you have nearest neighbor exchange. And you can, of course, obtain the dynamics for these individual rotors from this Hamiltonian by just using the usual Poisson bracket equations, which will give you the sort of very standard dynamics, which tells you that each spin feels a torque from its nearest neighbors because you have nearest neighbor exchange coupling. Okay, so that's a fairly simple system, but it turns out that it's, despite its simplicity, it's a fairly interesting system. So, but before I go on to, what's interesting about the system, let me also make this one remark, which I can't help making because my field of research is mainly quantum condensed matter physics, that it turns out that the quantum counterpart of this system is actually quite different. So by quantum counterpart, I mean now think of these as quantum spins, specifically spin halves. And then it turns out that this quantum Hamiltonian is fundamentally different from the classical one in the sense that this is an integrable system. It actually has an extensive number of conservation laws, whereas the classical system does not. And so in some sense, the classical system is thus more generic, and the lack of integrability of the classical system is also an indicator that it is that it is likely to thermalize at arbitrary energies, which incidentally does not happen for the corresponding quantum system. Okay, so I mentioned that one can use the lack of integrability as a proxy for thermalization in the classical system, but one can do a little better than that and actually provide other pieces of evidence for thermalization. So one of these is the presence of diffusion in this classical system, and diffusion as characterized by the existence of non-zero conductivities, which can then be converted into diffusion constants using some kind of Einstein relation. So here's here are some numerical calculations which have been done of the thermal conductivity from which you can extract the thermal diffusivity of this model, with temperature being a proxy for the energy of the system. So these are really calculations that have been done for isolated systems, but then, because they thermalize, you can convert the energy into temperature. And you can see that you actually have a non-vanishing, non-infinite thermal conductivity at over a wide range of temperatures, indicating the presence of diffusion. So this is one sort of piece of evidence for thermalization in these systems. More recently, there have also been studies of the spreading of chaos in this classical system. In fact, a very important piece of work in this particular direction was done at this institute. And the idea is that you calculate something called a decorrelator, which is really an object which tells you how much trajectories in phase space. Of course, you have to be careful when you define trajectories for the system, because the fundamental degrees of freedom are spins and not canonically conjugate variables. Nevertheless, you can think of trajectories in phase space and how much trajectories in phase space actually diverge from each other when you start them out with initial conditions which are very close. And so that can be quantified in terms of this object called a decorrelator. And what is found for this model is that if you start the system out with initial conditions which are very close in the sense that they're identical at all spins along the chain, except for one spin which is sitting at x equal to 0, and you calculate this object as a measure of the divergence of trajectories, what you see is that this initial disturbance actually spreads ballistically, and you have this red and blue region which is separated by a ballistically propagating front, and so you have sort of a large difference in the spin configurations within this red region and a small difference outside the red region, and in fact you have an exponential fall off of this decorrelator as you go across this front, from which you can extract a Lyapunov exponent, as I'll show you later. Okay, so this is interesting because the system, as I said, thermalizes. So if you were to look at regular two-point correlators of conserved quantities, you would actually see diffusion, which is shown on this plot. However, you do also have this ballistically propagating front, which corresponds to this spread of chaos with a velocity which has come, which is like a butterfly velocity, because this tells you how chaos is spreading in the system. Okay, so with that, let me now come to the system that we have studied, which is really a non-reciprocal version of this Heisenberg model. And so if I just go back a few slides, when you write down the equation of motion for the Heisenberg model, this is what you get with a plus sign here. And so we have been looking at a model in which the plus sign is replaced by a minus sign. And it turns out that this model was previously studied in this particular context by Sriram and Madan, who's also in the audience, where they were looking at what would happen generically if you had a system of spins, but you were driving a current in the system, so that you actually distinguished left from right because of the direction of the current. And one of the conclusions that they came to was that you would actually get, in the equation of motion, the sort of asymmetric exchange and non-reciprocal dynamics. And so the consequence of having this is the torque on spin I due to I plus 1 is actually equal to the torque on I plus 1 due to I, as opposed to being equal and opposite, which is what would happen for the Heisenberg model. The important thing is that you cannot derive dynamics like this, non-reciprocal dynamics like this, from a Hamiltonian, as opposed to Heisenberg dynamics. And so the questions that we've asked here is, if you have this non-reciprocal model, is there any notion of thermalization in this system, analogous to what you see in the reciprocal model, in the Heisenberg model? And also, is there any kind of chaos spreading in this system? Can you talk about a Lyapunov exponent or butterfly velocity? So is there an analogy with the Heisenberg system of this particular model? Okay, so for the Heisenberg model, we know that there are conserved quantities. In fact, those are the ones which display diffusion. And in the Heisenberg model, the magnetization is conserved. And there is also an energy from which you can derive the dynamics. So there's a conserved energy. It turns out that there are analogs of both of these quantities in this model as well. So instead of the magnetization, it's the staggered magnetization that was actually conserved in this model. And similarly, there is a staggered version of the energy, which turns out to be conserved, which we call the pseudo energy. So you can show that this dynamics actually conserves both of these quantities. Note, however, that even though you can write down a pseudo energy like this, you cannot derive the dynamics from considering the pseudo energy to be a Hamiltonian using the usual Poisson bracket structure. So this model is manifestly non-Hamiltonian. But it turns out that there is still a Liouville theorem for the dynamics, despite the fact that it's non-Hamiltonian. And there are some consequences of that, which I won't get into right now. Okay, so that's the model that we are looking at. And so there is, at this point, this analogy with the Heisenberg model in terms of the presence of these conserved quantities. Now, I should say that there's of course been a lot of recent interest in classical non-reciprocal systems, and this is by no means an exhaustive list of recent pieces of work looking at the physics of non-reciprocal systems. In fact, at this meeting itself, I think there are probably 4 or 5 other talks which deal with various aspects of non-reciprocality coming from activity and driving, but I thought I'd just mention some of these. Okay, so back to the model itself. So as I told you, the Heisenberg model displays diffusion in the conserved quantities. And we've identified conserved quantities for our model. So one obvious question to ask is whether there's any diffusion in these conserved quantities. So before I show you the numerical data, let me try to give you an analytical argument, or rather outline for you an analytical self-consistent calculation, which argues that there is diffusion in this model, and also that there is relaxation for the non-conserved quantity, which is the magnetization. So the idea is that we start from dynamics like our dynamics, which is this, and then we coarse grain the model to obtain a hydrodynamic description of the system. And the way that we do this is by expressing the equation of motion in terms of the staggered magnetization and the magnetization on every alternate bond. So by defining the staggered magnetization and the magnetization on every alternate bond, one can actually back out from these quantities the values of the spins at every site. So we can define these quantities Ni and Mi, and of course this is the conserved quantity. This is not. In our model, the regular magnetization is not conserved, and it turns out that you can write down the expression for the pseudo energy, which I mentioned earlier, also in terms of N and M, which I haven't done here, but I'll show you the coarse grained version of that in a couple of slides. Okay, actually on the next slide. Right, so having defined the staggered magnetization and the magnetization, we can now go ahead and coarse grain the model. And so basically write down the model as a continuum, keeping only the most relevant lowest gradient terms. And so sure enough, we get a conservation law for the staggered magnetization, as we should. And the magnetization to lowest order in the gradients has this particular form, the equation for the magnetization. And similarly, the staggered energy, the pseudo energy, which is conserved, has this coarse grained form, and it also has a conservation law, as it should. So this is what we get for this model when we coarse grain and keep terms to lowest order in the gradients. So now what we can do is we can do a self-consistent calculation to try to argue for the existence of diffusion in this model. And so what we are saying is the following, that in coarse graining and writing down the previous equations, we had kept terms to lowest order in the gradients. But then, as with any other such isolated model in which you're trying to do hydrodynamics and you're trying to put noise into the hydrodynamics, the noise comes really from the long wave number modes, which you've sort of thrown out in the lowest order gradient expansion. And so what we assume here is that those give you, at the level of the equations of motion for these fields, the following effects. So they respect the conservation laws. So even though you have noise, you still have the staggered magnetization conserved in this model. So the noise that's generated by the long wave, the large wave number modes is a conserving noise for the staggered magnetization. And of course, they can give you an effective coupling in front of this term. You could have some renormalization of the one sitting here due to these large wave number modes. So this is what you would expect, if not for any other reason, on phenomenological grounds for the staggered magnetization. And similarly for the magnetization, again, you would get noise, but generically that would be non-conserving noise because the magnetization is not conserved, and of course you could get some renormalized couplings. So taking into account the effect of the high wave number modes, this is the dynamics that we can write down for these two fields. And then what we can argue is that this dynamics gives us diffusion for the conserved quantity N and a relaxation for the non-conserved quantity M. So we make this ansatz, and we can actually write down, we can actually calculate the diffusion constant and the relaxation time self-consistently in terms of these couplings and the noise, or rather the strengths of the noise. And so for that, we can develop a diagrammatic formalism. So that essentially boils down to calculating the propagator for the magnetization which is not conserved and for the staggered magnetization which is conserved. And the diffusion constant for this and the relaxation time for that are sitting in the self-energy. So you basically look at the hydrodynamic limit of the self-energy, the low wave number, low frequency limit, and that should yield for you the relaxation time for the magnetization and the diffusion constant for the staggered magnetization. And again, as I said, the noise for the magnetization is non-conserving, and the noise for the staggered magnetization is conserving. So we can define these quantities and also then come up with a diagrammatic scheme to include them in this self-consistent calculation. So let me just very quickly, without going into details, show you the diagrams which contribute to lowest order, to one loop order, for the self-energy of the magnetization and the staggered magnetization. So these are the diagrams. And here lambda is a UV cutoff. So you can think of lambda as being the scale over which we actually coarse grain. So the self-energy for the magnetization is a sum of these two. And the self-energy for the staggered magnetization is a sum of these two. And you can see that these are the lowest order one loop contributions. You can indeed see that for the staggered magnetization, the self-energy does have this diffusive form. It's minus q squared times something, and that something can be read off as a diffusion constant. Whereas here, this actually has the form of just a relaxation time. So you can you can add these and think of the reciprocal of that as a relaxation time. So there is a way in which one can self-consistently argue for the existence of diffusion, and for the staggered magnetization and relaxation for the magnetization. Okay, so now you can say, well, having developed the self-consistent formalism, can you actually check that the microscopic model, the model for which we've written down the dynamics, does indeed have these properties? So this is a numerical calculation of the two-point correlator of the pseudo energy and the staggered magnetization, the two conserved quantities in this model. And I apologize for the font size and yeah, I mean, we're trying to sort of generate better figures, but the important thing is that both this and this actually display a nice diffusive form. You can collapse all of these curves for different system sizes onto a single curve using diffusive collapsing, and from which you can actually obtain a diffusion constant both for the staggered magnetization and the pseudo energy. I outlined the calculation, the self-consistent calculation for the diffusion constant only of the staggered magnetization. One can do a similar calculation for the pseudo energy as well. And so the staggered magnetization and the pseudo energy actually display diffusion. There's a nice scaling collapse, and you also get the characteristic scaling exponent of t to the 1/2, which is what is actually shown in this inset here. As far as the magnetization is concerned, which we argued relaxes, that was not conserved. So if you do the numerical calculation starting from different initial conditions, this is what you get. So it's a little messier than the staggered magnetization in the sense that it doesn't seem to give you a nice sort of exponential relaxation. There are bounces that you see. Nevertheless, it does appear that the magnetization is relaxing to a value which is 0. I mean, so you'll be plotting here the modulus of the magnetization. Any component of the magnetization is expected to relax to 0 and then sort of oscillate about that value because of noise. So you do see a relaxation from which one can sort of think of extracting a non-zero relaxation time. So these seem consistent with our hypothesis for what would happen when we co-screen the model. Just for the sake of comparison, if we look at the regular Heisenberg model and look at its conserved quantities, which are the energy and the magnetization, those also display diffusion. And there is again a scaling collapse for the energy and the magnetization of the regular Heisenberg model, from which you can extract the diffusion constant for these quantities. And this is again in some sense similar to the calculations that I showed you earlier, which had been done to calculate the thermal conductivity, from which one can extract the thermal diffusivity. And this is sort of in some sense a more direct extraction of the diffusion constant for the Heisenberg model. And so our model has exactly the same behavior, but for its conserved quantities. Okay, so let me now come to the decorrelator. So as I mentioned, the decorrelator is something which characterizes the spread of chaos in this system. And so you basically start the system out with two initial conditions which are very close to each other. And in this particular case, close means that they differ in terms of the spin configuration only at one site, and the spins at all the other sites are exactly identical in the two configurations. And so that's your initial disturbance at time t equal to 0. and then you can calculate this quantity, and these are heat maps of this decorrelator. When the decorrelator is, where the decorrelator is large is where this initial disturbance has spread, has reached. And so you can see that both for our model, the non-reciprocal model, and for the Heisenberg model, you actually do have this ballistic spread of chaos. You have a red region, which is where the disturbance has reached, nicely separated from a blue region where the disturbance hasn't reached, with a linearly, a ballistically propagating front between them. And it turns out that you can actually fit an expression for the spatial and the temporal dependence of the decorrelator in the vicinity of this front, which has this form, from which you can read off a Lyapunov exponent alpha and also this butterfly velocity Vb. So in general, of course, you would expect this to have the form exponential. I mean, if it has a Lyapunov exponent, you'd expect it to have the form exponential alpha t times, and and if it has this ballistically propagating front, times some function of x divided by vbt. It turns out that the best fit actually is to a quadratic function, from which one can extract a butterfly velocity and a Lyapunov exponent for each of these two models. I've not written down their values. So it turns out that the butterfly velocities and the Lyapunov exponent for the two models are not identical, but there's no reason for them to be identical either. I mean, one can at best argue that there is a velocity scale in both of these models, which is the same because we're taking the exchange coupling to be the same, and every velocity in the model has to be proportional to that. But the constant of proportionality, the number, could of course depend on the specific model. And so, we see exactly the same kind of behavior in terms of chaos spreading in our non-reciprocal model as in the Heisenberg model. Okay, so as I said, because I mainly work on quantum condensed matter, there's another slide that I can't help but show, which is asking what would be the quantum analog of this non-reciprocal model. So the the quantum analog of the reciprocal model in some sense is something that I've already alluded to. You just write down the Hamiltonian in terms of spin half operators, and then you can write down an operator equation for these spin half objects, and that's your quantum model. The problem with the non-reciprocal model is that there isn't any quantum Hamiltonian either that you can write down, from which you can get the equation of motion for these operators in terms of commutators, the way that you normally do in quantum mechanics. And so to understand what might be going on in the analogous quantum model, what one can do is one can just look at two spins. Look at a much simpler version of this model, which only has two spins. And so the non-reciprocity of this model with two spins is reflected in the fact that when you write down the equation of motion for these two spins, the right-hand sides are identical. So it's S1 cross S2, both for ds1 dt and ds2 dt. For the Heisenberg model, it would have been S2 cross S1. So this happens classically and quantum mechanically. However, here we are thinking of these now as being quantum mechanical operators. And so you can say, well, and you can see from this that the staggered magnetization is conserved. The difference between S1 and S2 is conserved and not the sum. And so you can say, well, you have two spins, and these are, let's say, spin half objects. So each one of them has a two-dimensional Hilbert space. This is your dynamical equation of motion. You see that S1 minus S2 is a constant. What could, how ugly could this thing be? I mean, this seems like a very simple model, but it turns out that it's anything but that. So you could try to numerically solve these equations for these two spins, initializing these two spins to be just regular quantum mechanical spin half objects, regular Pauli matrices, and ask what happens when you let the dynamics, when you let the system evolve according to the dynamics. And it turns out that all hell breaks loose. So not only is the commutation relation among the spins not conserved, which is like saying that in the classical system, the Poisson brackets between the spins would not be conserved, but there's something else which happens quantum mechanically, of which there's no simple classical analog, which is that the hermiticity of the spins, the fact that these are Hermitian operators, that also goes away. So the dynamics doesn't even preserve the hermiticity of the spins, and I can't really think of any simple classical analog of that. So In short, because there's no Hamiltonian, this is not quantum mechanically, this is not unitary evolution, it's non-unitary evolution. And so you can ask whether there is any quantum mechanical framework in which you can actually derive the sort of equation of motion. And one possibility is, and I'm saying, and I'm only mentioning this at the level of a possibility because we haven't explored this, I just have one more slide after this. Much beyond this, the fact that it's non-unitary evolution might indicate that there is a non-Hermitian Hamiltonian from which one could perhaps derive these equations of motion for these operators. And if that happens, then maybe there's also some implication for what that would mean classically in terms of what the Liouvillean of the system would do. But at the moment, this is just conjecture. And this is something which we are thinking about a little bit more. Okay, so anyway, so this brings me to my conclusion slide. So what we've done is we studied the dynamics of a non-reciprocal classical spin chain. And so the spin chain has conserved quantities analogous to the ones for its reciprocal counterpart. And then we can formulate hydrodynamics for this to self-consistently argue for diffusion for the conserved quantities, at least for the staggered magnetization, and relaxation for the regular magnetization. And we've numerically confirmed this, the existence of diffusion and relaxation in this model. And what we see is that the model also exhibits the spreading of chaos like its reciprocal counterpart. So in some sense, the punchline is this, that if on the basis of this kind of evidence, you argue that the reciprocal model thermalizes, then there is clearly an analog of the sort of thermal behavior, even for the non-reciprocal model, even though there is no energy that you can write down. There's no Hamiltonian that you can write down for the system. But at least in terms of the behavior of the conservation laws and the spreading of chaos in the system, one can make an argument for an analog of thermalization existing in this non-reciprocal model. And we're also in the process of trying to understand this a little better. What would this, in quotes, thermal steady state actually be for this non-reciprocal model? So all that is ongoing work. So thank you very much for your attention.
Questions?
Yes. So in the last part, how would the non-reciprocity affect entanglement?
Sorry, how does it?
How would it affect entanglement?
The entropy?
Yeah.
Okay.
Entanglement.
Oh, the entanglement.
In the last part, yeah.
Oh, the entanglement.
Yes,
right.
For the non-reciprocal.
Oh, for the non-reciprocal model.
Yeah.
Right, okay. So when you say how does it affect the entanglement, okay, let me just go, okay, how do I go back to, right. So there, of course, we have to think of starting with some entangled, say, non-entangled state and evolving it, okay? Now, the issue with doing that is normally for a reciprocal model, the way you would evolve it is using a Hamiltonian, and then you have unitary evolution. Here, of course, we don't know what that is, right? What would be the corresponding evolution operator? Because we are working completely at the level of operators here and not at the level of states. So I don't know if I have a good answer to your question in the absence of knowing what the evolution operator would be.
Any other questions?
Yeah. Sorry, I can take them.
I was curious about the connection you mentioned with this Liouville's theorem for non-reciprocal systems. Is there a connection between the conserved quantities that you mentioned, the staggered magnetization and the energy? And
well, okay, so all that I meant by there being a Liouville theorem for this system is that if you look at the flow of the system in phase space, it is incompressible. So if let's say I define a velocity in phase space along, for each of the components Sx, Sy, and Sz, then the S divergence of that velocity is equal to 0. I don't think that is contingent upon there being these conserved quantities any more than I can think of sort of the reciprocal system and maybe well, okay, so I mean, so I guess if I take the reciprocal system and I, say, apply a magnetic field to it, then that destroys the conservation of of all components of the magnetization, right? Then you only have conservation of sort of one component of the magnetization. Nevertheless, you will still have this incompressible flow for the reciprocal system. And so similarly, even for the non-reciprocal system, if you mess with it to destroy the conservation laws, that will not automatically affect the Liouville theorem for it. I mean, that should still be there.
Great. Thank you.
You just mean the diffusive transport, diffusive
Well,
relaxation.
okay, so okay, that's a good question. I mean, so I've been using a lot of
not e to the minus beta e for the final
not related to
e to the minus beta e, the final steady state distribution.
Okay, so I've actually been using a whole bunch of proxies for thermalization here, right? I've talked about the existence of diffusion being a proxy, with the spreading of chaos. Now, you can ask, what does it mean in general for something to thermalize? So one thing which in principle could be done, hasn't been done for the Heisenberg model as far as I know, and we've certainly not done it for our model, is that you could start with some initial state and just let the system evolve, and then look at what's happening to, characteristic physical observables of the system at long times, and are those equal to microcanonical averages as set by the conserved quantities. And so, right, so in principle, I guess that can be done. I'm a little surprised that it hasn't been done for the Heisenberg model yet. Maybe when we try to do it for our model, we'll see that there's some numerical issues with doing it, but that would probably be a better test of what thermalization actually, whether there's thermalization in this model rather than using proxies. But
If there's no further question, let's thank Subroto again. And our next speaker.